Swayam Prabha. Digital India. Educated India.
Hello and welcome. Let's continue our discussion on B-spline segments and curves. In particular, we are trying to design B-spline basis functions. Let's look at the example that we had discussed in the previous lecture. We computed a composite piecewise continuous cubic B-spline basis function using polynomial splines. This is how this cubic function will look like. Recall that we had used a few conditions. The position, slope, and second derivative at this point is 0. The position, slope, and the second derivative at this point are 0. And this B-spline basis function is non-zero over this knot span. This knot span has 1, 2, 3, 4, 5 knots. Also recall that we had called this basis function as a fundamental spline because the 4 knot spans were essential to provide the minimum support for this basis function. Notice that this basis function was composed of 4 individual pure cubic segments. What do you have to say about the continuity conditions at these 3 junction points? You're right. The position, slope, and the second derivative are continuous here. It's continuous here, and the 3 are continuous here, which would make this basis function a C2 continuous basis function throughout the span of T. In the sense, for T going from minus infinity to plus infinity, this will be C2 continuous throughout. In the previous 2 lectures, we had also seen that it was very inconvenient for us to compute the B-spline basis functions using polynomial spline. And because of that, we are going to be seeking alternative methods of computing basis functions. Let's look at one of them today. So today's lecture is about computing B-spline basis functions using Newton's divided difference approach. This is lecture number 21. First, a little recapitulation on the Newton's divided difference approach. Remember that we had discussed this method briefly when talking about curve interpolation. So let's say we start with Newton's polynomial. I hope you remember what that is. Just in case if you don't, here is a recap. The polynomial y is written as p of x, which is alpha 0 times alpha 1 times x minus x0 plus alpha 2 times x minus x0 times x minus x1, and so on and so forth. Up till the last term, alpha sub n minus 1 times x minus x0 times x minus x1 up till times x minus x minus 2. So given x0 y0, x1 y1, x2 y2 up till xn minus 1 yn minus 1, we should be able to compute Newton's polynomial. Alpha 0, alpha 1, alpha 2 are unknown coefficients at this time. Also recall how we computed these unknown constants. If we substitute y as y0 for x as x0, all these terms vanish. Only alpha sub 0 remains, which is equal to y0. Second step, if we substitute for x1 y1, we have y1 equals alpha 0 plus alpha 1 times x1 minus x0. All these terms starting from the third term over here, they'll vanish. We already know alpha 0. We would be able to compute what alpha 1 is. Likewise, using the third data point, x2, y2, we have y2 equals alpha 0 plus alpha 1 times x2 minus x0 plus alpha 2 times x2 minus x0 times x2 minus x1. All the other terms will vanish. We have alpha 0 from here. We have alpha 1 from here. We can compute what alpha 2 is, and so on. This way, we would be able to compute all these unknown coefficients up till alpha n minus 1. Can you tell me about the degree of this polynomial? You should be able to figure it out. This is the linear term, this is the quadratic term, and this would be the term corresponding to degree. You would know it better. Would you say this term would correspond to degree n minus 1 in x? Anyhow, let's move forward. Notice what alpha 0 would depend on. Alpha 0 would depend only on y sub 0. Alpha 1 would depend on the first two data points, in particular y0 and y1. Alpha 2 would depend on the first three data points, y0, y1, and y2, and so on. Using this observation, let me introduce some notations here. In general, we can express this dependence as follows. Alpha I is equal to y within square brackets. Now this is important. Y within square brackets, function of x0, x1 up till xi. Let's try to go back here. Alpha 0, that is for I equals 0, would depend only on x0. For I equals 1, alpha 1 will depend on x0 and x1. For I equals 2, alpha 2 will have relation corresponding to x0, x1, and x2, and so on and so forth. We are using square parentheses to express the interrelation between the coefficients and the data point in the Newton's divided difference polynomial. So using this notation, we have alpha 0, which is equal to y within square parenthesis x0. This is equal to y0. Alpha 1 is equal to y within square parenthesis x0, x1. You would know what that is, which is y1 minus y0 over x1 minus x0. Now, how can you express y1 in terms of this notation right here? Y within square parenthesis x1 minus y within square parenthesis x0 over x1 minus x0. So far, so good. How about alpha 2? From this notation, we have alpha 2 is equal to y within square parenthesis x0, x1, and x2. And this is equal to 1 over x2 minus x0 times y2 minus y1 over x2 minus x1 minus y1 minus y0 over x1 minus x0. You would note that this is the second divided difference, and these two are the first divided differences. Now try to introduce this notation in this expression right here. y2 minus y1 over x2 minus x1 can be expressed as y within square parenthesis x1, x2. Try to relate this expression with this one here and raise the index by 1. y1 minus y0 over x1 minus x0 is the same as y within square parenthesis x0, x1, which is right here. And we borrow 1 over x2 minus x0 from here. Can you think of generalizing this? By observation or by inspection, it is possible. In general, alpha r can be written as y within square parenthesis x0, x1, x2 up till xr, and this is equal to y within square parenthesis x1, x2 up till xr minus y within square parenthesis x0, x1 up till xr minus 1 over xr minus x0. Let's see if it is true. Put r equals 2 here. So you get alpha 2 equals y of x0, x1 and x2. If r is equal to 2 here, we'll have y of x1 and x2, which is right here. And then this would be followed by minus y of x0 and x1, which is right here. When r is equal to 2, we'll need only x1. And in the denominator here, we'll have x of 2 minus x of 0. There's a nice way I remember this. What is important are the indices. This index, this index, this index right here, this index right here, and these two indices. Now this index is 1 plus the first index that appears here. This index is the last index. For this one, this is the first index that appears here. And for this last index, if you look at this index, I'll have to subtract 1 from it. So this is x of r minus 1. And then x of r, which is the final x here, minus x of 0, which is the initial x here. Okay. Now this is the story when I have data points starting from 0, 1 up till r. I should be able to compute the divided difference corresponding to any set of intermediate data points. How about for y within square parenthesis x sub s, x sub s plus 1, x sub s plus 2 up till xr? Remember what I told you right here. This index would correspond to 1 plus the first index. So the first index is s. This one here will be s plus 1. This index will correspond to the last index. Here, it is the first index in this interval. And for this one, I'll have to subtract 1 from the last index here over xr minus xs, which is xr minus xs here. With a little practice, you will be able to remember this. Now, this is the tabular form that we have seen in quite a few examples before. If you recall, I had worked a very simple example on board pertaining to Newton's divided difference method. And a similar approach was used when computing intermediate de Castelju points in case of Bezier segments. Let's revisit this method. Okay, but first, y within square parenthesis xs, xs plus 1, xs plus 2 up till xr are known as divided differences. They are the coefficients. And as I said, they can be computed in tabular form quite easily. You'll have to arrange the data column-wise. The first column would correspond to all the x values, x0, x1, x2, up till xn minus 1 or xn or whatever. The second column will correspond to all the y values. The third column will have the first divided differences. So what would make this second column here? The y values. They would be the 0th divided differences. The fourth column here would correspond to the second divided differences, and so on and so forth. The third divided differences for the fifth column. Anyhow, let's arrange first all the x values. x0, x1, x2, and x3 in this example. We are working with 4 data points. Correspondingly, we'll have y within square parenthesis x0. which is simply y0, y within square parenthesis x1, which is simply y1, this is y2, and likewise this is y3. How would you compute the first divided differences? You need to use only this information. This would be y of x0 and x1, which is y1 minus y0 over x1 minus x0. Likewise, the divided difference corresponding to this information here will be y within square parenthesis x1 and x2, which is y2 minus y1 over x2 minus x1. How about the third one? Can you tell me what this is? You guessed it right. This is y of x2 and x3. And this is y3 minus y2 over x3 minus x2. What's next? How do we compute the second divided difference? For that, we would need to use this information here. Let me give you the cue for the first one. The second divided difference will be y of x1, x2 minus y of x0, x1. Remember the notations that we had discussed previously, over x2 minus x0. What have I done here? I have considered the limits of this larger interval, and that would be equal to y within square parenthesis x0, x1 and x2. How about the second divided difference here? This would be y of x2, x3 minus y of x1, x2 over x3 minus x1. Once again, I have skipped x2 here and considered the limits of this larger interval. And this will be denoted as per our convention by y of x1, x2 and x3. And finally, the third divided difference for this example will be this number right here minus this number right here over a larger interval. This number minus this number. And can you now tell what the notation of this divided difference will be? This will be y within square parenthesis x0, x1, x2 and x3. It might be looking a little complicated for you to compute divided differences in this manner. We'll be working an example in this lecture, and hopefully that would help you consolidate the concept. So far so good with regard to the mathematics behind the divided differences. But physically, what would the divided differences mean? Consider a general polynomial curve. Let's say this is xs and this is y of xs, which is ys. Let's say we have another point xs plus 1. Correspondingly, the value is ys plus 1. Y of xs plus 1. Third point, xs plus 2, ys plus 2. Join the first 2 points here. This line will represent the slope in the discrete sense, of course. And the slope will be equal to ys plus 1 minus ys over xs plus 1 minus xs, which is the first divided difference using these 2 points. So the first divided difference will represent the local slope. Again, as you would see, this is denoted by y of xs plus 1. Likewise, we can do something very similar for the second and the third data point. the slope here is given by ys plus 2 minus ys plus 1 over xs plus 2 minus xs plus 1. And that is represented using our convention by y of xs plus 1, xs plus 2. So these are all local slopes represented by the first divided difference. How about the second divided difference? The second divided difference will correspond to y of xs plus 1, xs plus 2 minus y of xs, xs plus 1 divided by xs plus 2 minus xs. This would locally represent the second derivative of the curve. So in general, the n minus 1th divided difference would represent the n minus 1th derivative of the curve. Remember the term that I'm using here. It represents, it is not equal to the n minus 1th derivative of the curve. Now this is something very interesting. For an n minus 1th degree polynomial, the n minus 1th divided differences are all equal, and correspondingly the nth divided difference are all 0. Let me use this example and explain a few things on the board for you. Let me make up an example for you here. Let me consider a quadratic polynomial. Y equals, let's say, 5x squared minus 2x plus 3. Let me generate some data points and arrange them in the tabular form. So we'll have the x values, we'll have the y values. Let me take uniform values to make our lives simpler. 0, 1, 2, 3, 4, 5. For x equals 0, y equals 3. For x equals 1, we'll have 5 minus 2, which is 3, plus 3, which is 6. For x equals 2, we'll have 5 times 4, 20, minus 4, 16, plus 3, 19. For x equals 3, this is 9 times 5, 45, minus 6, which makes it 39, plus 3, 42. Looks like I'm going to be testing my mathematics here. For x equals 4, 16 times 5 is 80. 80 minus 8 is 72, plus 3, 75. Let's stop here. Let me consider this if I need to later. Okay. Now let me arrange the column for the first divided difference. I call it 1D D. How would I start computing those divided differences? I'll use the information corresponding to the first and the second row. And this will be 6 minus 3 over 1 minus 0, which is 1. So 6 minus 3, this is 3. Likewise, 19 minus 6 is 13 over 1. Okay. 42 minus 19. Okay, so let me compute 42 minus 20, which is 22, and 1 less, which would make it 23. 23 over 1 is 23. Likewise, 75 minus 42 would be 33 over 1. So this is 33. Okay, let me now compute the second divided difference. I call it 2dd. Now for this, I'm going to be doing 13 minus 3, which is 10, which is 10 over 2 minus 0, which is 2 here. This is equal to 5. How about the second divided difference corresponding to this information here? So this will be 23 minus 13, which is again 10 over 3 minus 1, which is 2. This is again equal to 5. For this one here, this is 33 minus 23, which is 10 over 4 minus 2. 2 again. This is equal to 5. Recall what I had previously mentioned. The second divided difference of a degree 2 pure polynomial are all equal, 5, 5, and 5. What do you have to say about the third divided differences? I call them 3dd. So this is 5 minus 5, 0 over. Now I'll have to be a little careful here. I'm going to be enlarging my interval. So this would be 3 minus 0, which is 3. This is 0. Likewise, 5 minus 5, again 0, over 4 minus 1, 3, which is 0. Every time I compute the subsequent divided difference, I'll have to enlarge my interval here by 1. Keep that in mind. Okay. What did I tell you before as well? The third divided difference corresponding to a degree 2 pure polynomial are all 0. In general, the n plus 1th divided differences corresponding to a degree n pure polynomial will all be 0. You can test it out for as many cases you want. I find it a lot comfortable to compute the Newton's divided differences this way. You must be wondering how the Newton's divided differences are related to B-spline basis functions. How are we going to construct B-spline basis functions using these divided differences? I'll come to that a little later. But first, let me also give you an algebraic form of divided difference. So y within square parenthesis x sub j plus 1 up till x sub j plus k is written as summation and index r going from 0 to k of y sub j plus r over w prime. This probably is not clear. W prime, that is the first derivative of w. I'll talk about that in a while. W prime evaluated at x j plus r. So consider a function w of x equals x minus xj times x minus xj plus 1 up till x minus xj plus k. And w prime x is the first derivative of w with respect to x. Too many indices, and it might not be very clear to you in first go. Once again, try to remember these terms. So here index r goes from 0 to k. K corresponds to the last index j plus k. So this is k here. Y of j plus r. R is going from 0 to k. That would mean that we are considering the y's corresponding to xj, xj plus 1 up till xj plus k over w. How you would want to construct w? W is these terms here, x minus xj times x minus xj plus 1 and so on and so forth up till x minus xj plus k. In a sense, all you need to do or remember is subtract all these terms xj, xj plus 1 respectively from x and multiply these terms to construct w. Differentiate w once with respect to x and evaluate w prime x at xj plus r. Let me give you a few examples that will help you understand and remember this a little better. For example, when k is equal to 0, we are talking about y of xj alone. So y of xj is equal to y of x. R is 0 here. Y of xj over w prime of xj. What is w prime of xj? Is the first term here, x minus xj. Differentiate this once to get 1. So this is y of xj over 1, which is simply yj. How about for k equals 1? We have y within square parenthesis xj, xj plus 1 right here. The numerators for these two terms will be yj and yj plus 1, yj and yj plus 1. The denominators will be w prime evaluated at xj and w prime evaluated at xj plus 1 right here. How do you construct w? W will be x minus xj times x minus xj plus 1. Differentiate that once to get w prime x equals x minus xj plus 1 plus x minus xj. So w prime of xj is xj minus xj plus 1 and w prime at xj plus 1 is xj plus 1 minus xj. This term goes off. Substitute for those terms here. So y of xj, xj plus 1 equals yj over xj minus xj plus 1 plus yj plus 1 over xj plus 1 minus xj. So this term here is a negative of this term. So this would make this term on the left hand side equals y sub j plus 1 minus yj over xj plus 1 minus xj. And this expression is very familiar to you by now. For k2, how many terms will you have here? 3. So y of xj, xj plus 1, xj plus 2 within square parenthesis. This is denoting the second divided difference here. This would be equal to yj over w prime at xj plus yj plus 1 over w prime at xj plus 1 plus yj plus 2 over w prime at xj plus 2. How about w? In this case, w will have 3 terms in x. If you think about this, the second divided difference corresponding to the data points j, j plus 1, j plus 2 can be written as y of xj plus 1, xj plus 2 minus y of xj, xj plus 1 over xj plus 2 minus xj. Coming back to w here, w is constructed using these three terms corresponding to xj right here, xj plus 1 right here, and xj plus 2 right here. You know how to differentiate this once. Evaluate the result at xj, xj plus 1, and xj plus 2, and substitute those results back. What I have told you is only the algebraic expression corresponding to this divided difference here, y over xj, xj plus 1 up till xj plus k. I have not yet derived this expression for you. You might want to consider this as an assignment, and I'll give you a cue as to how to derive this expression. I would suggest that you use mathematical induction for derivation. You probably would have studied this technique in your first year or second year of undergraduate mathematics. Start with y at xj. Maybe try to convince yourself with the first two divided differences, and we have already done this exercise here. Assume that this expression is true for, say, y equals xj, xj plus 1 up till xj plus k. And using this result itself, try to compute the next divided difference, which is y of xj, xj plus 1 up till xj plus k plus 1. And try to show that using this result itself, you are able to accurately compute the subsequent divided difference. This is mathematical induction for you. Why don't I work an example for you on that? This will help you consolidate the algebraic form of the divided difference. It is important for you to understand this because we will be needing these concepts later on when we discuss B-spline basis functions. Let me make up an example. So say I'm going to use 4 data points. 0 data point is, let's say, 0, 1. The first data point is, let's say, 2, 3. The second data point is, let's say, 3, 5. And the fourth data point here is, let's say, 5 minus 2. I'll have these 4 data points. Correspondingly, I would be able to compute up till the third divided difference. Let's try to compute directly using the algebraic form. So y of x0, x1, x2, and x3 y of 0, 2, 3, 5 is equal to summation, the index r going from 0 to 3, y sub j plus r over w prime x j plus r. Let me write this thing in elaborate form so that we all understand. Now j here is 0. So we'll have y0 over w prime evaluated at x0 plus y1 over w prime at x1 plus y2 over w prime at x2 plus y3 over w prime at x3. Now we know what these values of y0, y1, y2, and y3 are, which are 1, 3, 5, and minus 2 respectively. Let's try to first construct w and then evaluate these denominators. So w here is equal to x minus x0, x minus x1, x minus x2, and x minus x3. We know what x0, x1, x2, and x3 are. Let's plug in those values directly. This is x, x minus 2, x minus 3, x minus 5. Now, w prime x equals total w over total x. We can differentiate this expression as follows: x minus 2, x minus 3, x minus 5 plus x, x minus 3, x minus 5 plus x, x minus 2, x minus 5 plus x, x minus 2, x minus 3. Essentially, differentiate this expression considering the first derivative of each of these terms one at a time. Retain the other three terms, differentiate the first term to get this, retain the first, third, and the fourth term, differentiate this term to get the second term here, and so on and so forth. You would know this. Keep this expression ready in your notebook. We will be needing this. Okay, so what I have done is I have copied this expression here. Now, what is w prime at 0? So the second, third, and fourth terms will all be 0. It is this first term which will be non-zero here. This is equal to 2 times 3 times 5 with a negative sign, minus 30. How about w prime at x equals 2? Which corresponds to this term here. Now here, if you notice, this term will vanish, this one and this one, they'll all vanish. What am I left with? This is equal to 2 times 2 minus 3, which is minus 1, and 2 minus 5, which is minus 3. This is equal to 6. W prime corresponding to x2, which is 3, is equal to this term, and this term. They'll all go, and it's only the third term that will remain. This would correspond to 3 times 3 minus 2 is 1, and 3 minus 5 is minus 2. This is minus 6. And finally, w prime at 5 is equal to the terms corresponding to the last term here. This, and this, they'll all vanish. 5 times 5 minus 2 is 3, times 5 minus 3 is 2. This is equal to 30. And so, y of 0, 2, 3, 5 is equal to y0, which is 1 here, over w prime at 0, which is minus 30, plus y1, which is 3 here, over w prime 2, which is 6, plus y2, which is 5, over w prime 3, which is minus 6, plus y3, which is minus 2, over w prime at 5, which is 30. You can work out the math and simplify this to get a number. And try to compare what you get with a number that you would get when you're using the tabular form to compute the Newton's divided differences. Let me try to simplify this for you and see if I can go any. So if I take the least common factor, which is 30, I get minus 1 plus 15 plus 25. I think I'll have a minus sign here. Minus 2. This is equal to minus 10, minus 11, minus 13. Minus 13 over 30. Now let me use the tabular form to see if I get to the same number. Arrange all x's in a single column, 0, 2, 3, and 5. Arrange all y's in the next column, 1, 3, 5, minus 2. And then, so these are the x's, these are the y's, and then start computing the divided differences. So the first divided difference, combine these two, 3 minus 1 over 2 minus 0, which is 1. Combine these two, 5 minus 3 is 2, 3 minus 2 is 1, so this is 2 over 1, which is equal to 2. Minus 2 minus 5, which is minus 7, over 5 minus 3 is 2. Coming to the next one. 2 minus 1 is 1 over, now I'll have to enlarge the interval here, 3 minus 0, which is 3. Likewise, combining these two, minus 7 over 2 minus 2 over 5 minus 2, which is 3. I can simplify this as minus 11 over 6. And the final divided difference is minus 11 over 6 minus 1 over 3. I'm going to multiply and divide by 2 here. So this will be minus 2 over 6 over this entire interval, which is 5. And this would be equal to minus 13 over 30. So you just saw that we got the same number. It doesn't really matter if we use the tabular form or the algebraic form. they would give you the same result.